Most AI agents run in the cloud. They need a server, a runtime, an internet connection, and usually a monthly bill. What if you could take that agent, the part that listens, reasons, and acts, and shrink it down to a chip the size of a postage stamp? That's exactly what we're doing today. We're going to deploy a fully autonomous AI agent onto an ESP32 S3 microcontroller. This chip costs about $10. It fits in your hand, and once it's flashed, it can receive natural language instructions, reason over them using a local language model, and physically actuate hardware, lights, sensors, alerts, without a single line of code from you. The framework is called ESP-Claw. It was built by Espressif, the same company that makes the ESP32. And it's the most interesting thing I've seen in Edge AI this year. Let's build it. ESP-Claw is an AI agent framework designed specifically for microcontrollers. The core idea is something they call chat as creation. Instead of writing firmware, you describe what you want in plain language. The language model translates your instructions into Lua scripts, and those Lua scripts run directly on the ESP32's hardware. Here's why that architecture matters. The LLM, the part that understands your words and reasons about what to do, runs on a gateway. That's a PC, a Raspberry Pi, or Cloud VPS. The ESP32 never touches the LLM directly. It just receives executable Lua and runs it locally. This split keeps the chip lean and keeps your hardware loop fast, even if your internet connection drops. The safety implication is important too. The LLM never directly controls a GPIO pin. It generates auditable, human-readable Lua that a human can inspect before or after execution. You get the natural language interface without giving an AI direct write access to physical outputs. The board you want is the ESP32S3 Dev Kit SOUL.md. That specific variant, not the N8R8, not a generic ESP32 S3. The N16R8. Here's why the variant matters. The N16R8 has 16 megabytes of flash and 8 megabytes of PSRM. The N8R8 has 8 megabytes of flash and 8 megabytes of PSRM. That difference in flash is critical for over-the-air firmware updates. The ESP-Claw firmware partitions flash into 2 app slots for safe OTA rollback. On the N8R8, each app slot is limited to roughly 5 megabytes. Not enough headroom for the Lua runtime plus future firmware updates. You will hit this ceiling within weeks. The N16R8 also handles audio buffer processing more reliably at high throughput, which matters if you extend the agent toward voice input. The board costs between 600 and 900 rupees from Indian suppliers, roughly $7 to $11. It's a negligible cost difference compared to the N8R8, and the headroom it gives you is significant. One more detail. The board has 2 USB-C ports. Use the one labeled COM for flashing. That port routes through a dedicated UART USB bridge, which gives you reliable, stable data transfer during the initial flash. You don't need to install anything to flash this board. No Espressif toolchain, no Python environment, no Arduino IDE. Go to esp-claw.com in Chrome or Edge. It must be a Chromium-based browser because the site uses the Web Serial API. Plug in your board via the COM port. The site detects it automatically. Click Flash Firmware. The tool writes 3 partitions in sequence. The bootloader at address 0x1000, the partition table at 0x8000, and the main application at 0x10000. The entire process takes about 90 seconds. When it's done, the board resets and begins its pairing sequence. You'll see a Wi-Fi access point broadcast from a board. Connect to it from your phone or laptop, open the captive portal, and enter your home or office Wi-Fi credentials. Once connected, the board is live on your local network and ready for the gateway. The gateway is the brain of the system. It runs on your PC, a Raspberry Pi, or a VPS. It handles the LLM inference and acts as the translation layer between your natural language input and the Lua that runs on the ESP32. For the LLM, we're using Ollama. The command is Ollama launch openclaw -- model Qwen 2.5:7b. Qwen 2.57 billion parameters is the minimum recommended model for this use case. You need at least 8 gigabytes of VRAM and a 64,000 token context window. The model is free, runs entirely on your hardware, and sends 0 data to any external service. If you want stronger reasoning, Qwen 2.514 billion and DeepSeek R132 billion both work. They just need more VRM. The gateway exposes a local endpoint that the ESP32 calls over your Wi-Fi. The board sends sensor data and event context. The gateway sends back Lua. The loop is fast, typically under 2 seconds from trigger to execution on a local network. To give your agent a voice channel, a way to receive commands and send alerts, you connect it to Telegram. Open Telegram, search for BotFather, and send a command /Nabot. BotFather walks you through naming the bot and gives you an API token. Paste that token into your gateway configuration file and restart the gateway. Now, on your phone, open Telegram and send /start to your new bot. The gateway receives the message, generates a 6-digit pairing code, and logs it to your terminal. You enter that code back into Telegram. This out-of-band verification step confirms that the person talking to the bot is the same person who controls the gateway. Once paired, you can send natural language commands directly from Telegram. Turn on the red LED, alert me when motion is detected, run the door check sequence. The agent interprets and executes. The agent has persistent memory stored directly on the ESP32's flash. 3 files control its behavior. SOUL.md defines the agent's personality, how it should respond, its tone, any constraints on what it will or won't do. USER.md stores your preferences, your name, your time zone, your preferred notification format. MEMORY.md is long-term context, things the agent has learned about your environment and routine over time. These files are editable. You can modify them directly through the gateway interface or over the air. If your agent starts behaving unexpectedly, SOUL.md is the first place to look. If it's forgotten something you told it last week, add it to MEMORY.md. This is how you give the agent context without re-prompting from scratch every session. Think of it as a configuration layer that the LLM reads before every interaction, persistent, editable, and stored on the device itself. Let's look at 3 things the agent can do out of the box. First, GPIO buzzer. Send the message beep 3 times via Telegram. The gateway translates that to Lua, 3 calls to the GPIO output function with a delay between them. The ESP32 executes it and the buzzer fires. Response time, under 2 seconds. Second, RGB LED via PWM. Set the LED to purple. The Lua the gateway generates calls the LEDC peripheral. That's the ESP32's hardware PWM controller, with the correct duty cycle values for red and blue channels. No low-level register manipulation from you. The model handles the translation entirely. Third, and the most practically useful, PIR motion sensor to Telegram alert. Wire a passive infrared motion sensor to one of the ESP32's GPIO inputs. In your SOUL.md, tell the agent, if motion is detected, send me a Telegram message immediately. The agent registers an interrupt service routine on that pin. When motion triggers the sensor, the ISR fires, the gateway dispatches a Telegram message, and you get a push notification on your phone, typically within 1 second of the motion event. One more capability worth understanding. MCP, the Model Context Protocol. The ESP32 running ESP-Claw operates in 2 directions simultaneously. It's an MCP server. It exposes its hardware as tools that any external AI can query. A Claude agent running on your laptop can call read temperature sensor or toggle relay on the ESP32 as a structured tool call, the same way it would call a web API. It's also an MCP client. It can query other MCP servers on your network, pulling in live data from your calendar, your home automation system, or any other service that exposes an MCP endpoint. This is the part that makes ESP-Claw more than a demo. A $10 microcontroller becomes a hardware node in a larger multi-agent system, addressable, composable, and programmable in plain language. The total hardware cost for this entire setup is under $15. The software is open source. The LLM runs locally, and the natural language interface means you can extend the agent's behavior without touching firmware. If you're building physical products, home automation, or want to understand where edge AI is actually going, this is worth your time. Hardware links, the ESP-Claw repository, and Ollama model recommendations are all in the description.